Hi everybody, in this video I will talk about the Hydrate Lab. The main goal of the Hydrate Lab is to determine the empirical formula for the hydrated salt. For example, this is the empirical formula for copper 2 sulfate, and the goal of the lab is to find the degree of hydration labeled as X here, which is how many water molecules that are attached to the copper 2 sulfate. So let's now talk about how this is done. In a lab, you will have a Bunsen burner, which is this thing over here, connected to a tube that produces methane gas in order to provide the fuel that allows this fire up here to continue running, and that's what a Bunsen burner is. And over here off to the side, we have a ring stand, which contains the stand, of course, and this ring, which is like a circular thing where you put stuff on it. And in this ring, we place a triangular clay, which is this thing that allows us to place the crucible, which is this, I guess, this little pot. And this crucible will contain the hydrated salt. So I will draw the hydrated salt in blue. And after 1 or 2 or even 3 heatings, the water inside the hydrate will evaporate, and in the crucible you are left with an anhydrous salt, which I will draw in red. And in this process, water will of course escape, and the mass of the anhydrous salt will be less than the mass of the hydrated salt because some of the water in the salt left. So we do this in order to find how much water left, and this allows us to find the formula for the hydrated salt. So for example, if we place a hydrated form of sodium chloride and we heat it up, then it will separate to sodium chloride, the anhydrous form, and water, which will evaporate and become a gas, which is shown over here. So that is the gist of a hydrate lab, and usually there's a lid on top of the crucible in order to prevent the salt from jumping out, because when you heat salt, it tends to become chaotic and want to jump out of it. So that's why a lid is very useful. Now let's take a look at some data that I made up. So this student collected some data and wants to find the degree of hydration for copper 2 sulfate. So the student weighed the crucible and lid and found that it was 5.00 grams. And the student added the hydrated salt, which is copper 2 sulfate with an unknown degree of hydration, and found that the mass was 26.02 grams. Now we have to get the useful information from this, which is the mass of the hydrated salt. So how do we find this? Well, if we subtract the mass of the crucible and lid and salt minus the mass of the crucible and lid, we will get the mass of the hydrated salt, since these two cancel out, leaving the hydrated salt. So we would take 26.02 minus 5, and we would get 21.02 grams for our hydrated salt. Now the student heated this, and after the first heating, the student found that the mass of the crucible and lid and anhydrous salt was 24.73 grams. So how can we get the mass of just the anhydrous salt? Well, we could just subtract this value from this value in order to get the mass of the anhydrous salt. So 24.73 grams minus 5.00 grams is, let's see, I think it's 19.73 grams. Let's do this for the second and third heating too. 18.5 minus 5 is 13.50 grams, and 18.24 minus 5.00 is 13.24 grams. And we have gotten all the useful information we need. We've gotten the mass of the salts before and after. Now the next question is, Do we use the first heating, second heating, or third heating? Well, after the heating, you want to make sure that all of the water in the hydrate has fully dissociated from the hydrate. So you want to make sure that all of this turns into this. So in order to effectively maximize that, you want to heat it as many times as you can, because the more you heat it, the more H2O will escape. And because of that, you will get a more accurate answer for the amount of H2O that was in the hydrate in the first place. So the more you heat it, the more H2O you will get, I guess, in your calculation. So let's see how that applies. So before we do this, let's find out how much water escaped from the hydrate. So we know that we are going to use the third heating because our goal is to get the most accurate mass for our anhydrous salt, and in order to do that, we have to get rid of as much water as possible. So heating it more is better. So let's calculate the amount of water. If our hydrated salt has 21.02 grams and our anhydrous salt has 13.24 grams, this must mean that the difference is due to the water escaping. So this will be the amount of water that escapes. So if we subtract 21.02 by 13.24, we get that the amount of water is equal to 7.78 grams. So now that we have all this information, we can actually calculate the degree of hydration, and let me show you how that works. So calculating the degree of hydration is just like empirical formulas, because we are calculating the ratio between the moles of copper 2 sulfate and the moles of H2O. So if you're doing something like this, think of it as empirical formulas. So we have to calculate the moles of copper 2 sulfate without the water. So this is the anhydrous form. So the anhydrous form of the salt will have a mass of 13.24, which was the most accurate answer that we came up with because it's the third heating. So this will be only the salt, meaning the anhydrous salt. So we have to calculate the moles of copper 2 sulfate from this mass. So we know that the molar mass of copper 2 sulfate is 159.62. So we do 13.24 divided by 159.62. And I got that we have 0.082947, and since it has 4 sig figs and 5 sig figs, my answer will have 4 sig figs, but I will underline the fourth digit, or I mean the fifth decimal place, in order to define how many sig figs I have, which is 4. So this is in moles, and now let's calculate the moles of H2O. So to do that, we divide 7.78, which is the mass of the water, by the molar mass. So 7.78 divided by 18.02, and I get that we have 0.43174 moles of water. And notice how there are 4 sig figs. No, actually there are 3 sig figs here and 4 sig figs here. So our answer will have 3 sig figs. So let's underline the third decimal place to indicate where our sig figs are. So now that we have the moles, now let's find the simplest ratio between the two. So we are going to divide both of them by the smallest one. So the smaller of the two is this one. So we're going to divide by 0.082947. And as you will see later, the sig figs really don't matter in the end, but it's good to keep track of them because it's good practice. So if I divide 0.43174 by 0.082947, we get 5.2 to, oh wait, that's the wrong side. This is 5.2, and this is 1. So notice how this has to be 1 in order for it to work, because all the hydrates that we've seen so far have only, a 1 in front of the salt or the formula unit. So we see a problem here. We see that's 5.2. But to tell you the truth, in labs like these, you usually don't have that great of equipment, and as a result, your answers are never perfect. So, because this is a lab and not a homework problem, we can generally assume that 5.2 is close enough to 5. And that's just because maybe the person who did this lab didn't do a great job in calculating the masses, or maybe the student didn't heat it enough, or, there are many issues that can go on in a lab. So, in labs, expect to get answers that deviate and don't really match up, but you are allowed to round in labs because in the end, you just want everything to work out. So I'd say that for every 1 copper 2 sulfate formula unit, we have 5 waters. So we have thus solved the riddle. X is 5. So our salt is copper 2 sulfate pentahydrate. And that's how you do the Hydrate Lab. And I hope you've learned a lot, and thank you for watching.